is one of the most spectacular things you can experience. But what causes it? The answer to this question is equally spectacular, bringing together quantum mechanics and astrophysics. Let's start with what makes things glow. If you put some hydrogen in a tube and pass an electric current through it, it glows pink. Here's what it looks like in real life. This color is made up of a bunch of different wavelengths, which we can separate out using a prism. When sunlight passes through a prism, it separates into a rainbow of colors. You've probably seen rainbows like this from accidental prisms in your environment. A diffraction grating provides a similar effect using hundreds of microscopic slits. They're better than prisms for precise laboratory experiments. If you send hydrogen light through a diffraction grating, instead of a rainbow, what comes out is a few lines. That's weird. How come? Well, the tube is filled with hydrogen atoms, with electrons whizzing by due to the current. If one of these electrons collides with the hydrogen atom, it bumps the electron to a higher energy level. This is an excited state. And there are other excited states with even higher energy levels. But the atom has to get rid of this excess energy somehow. So after a few billionths of a second, the electron falls back and emits this extra energy in the form of a photon. Some photons are visible to humans. These are little packets of energy that we can see. A small drop produces a red-colored photon with less energy, while a bigger drop produces blue light. Cyan is in between. And even bigger drops produce ultraviolet photons, which humans can't see. Each photon has a wavelength, and together these produce the hydrogen emission spectrum that we saw through the diffraction grating. The combination of all these photons looks pink to our eyes. Every atomic element has a unique emission spectrum. For example, neon looks orange, helium yellow, and mercury produces a light blue color. For the rest of this video, we'll skip showing all these rings and just draw the atom with the color that it's about to emit. So what's the spectrum of the aurora? In 1867, Anders Angstrom pointed his spectrometer at an aurora and discovered that the green color has a wavelength around 557 nanometers. However, he wasn't able to identify its source. The answer eluded scientists for the next 50 years. Lots of theories were put forth, including nitrogen, argon, krypton, even a new element called aurorium. The answer turned out to be oxygen. You're probably thinking, duh, isn't oxygen pretty obvious? Our atmosphere is full of it. Not quite. The air we breathe is O2, a molecule of two oxygen atoms stuck together. But what lights up the aurora is atomic oxygen, which is nearly impossible to find on Earth. But even if you were somehow able to obtain a tube of stable O1 and excite it, you wouldn't see anything. An excited oxygen atom takes almost a second to release its green photon. This is like eternity in atomic timescales. And if a collision occurs during that time, no photon will appear. Instead, the energy is transferred in the collision. Since atoms in a gas are constantly colliding, none of these last long enough to emit a photon before they collide or merge into larger molecules. This is why you don't see oxygen emit green light on Earth. But in the upper atmosphere, the air is thin. There are fewer atoms. So excited oxygen atoms have enough time to emit green photons before colliding. Excited states like this, that last an unusually long time, are called forbidden. But where does this O1 come from? Atmospheric O2 absorbs ultraviolet and X-ray photons, which break it up into individual atoms. This creates a plentiful supply of atomic oxygen in the upper atmosphere. In a very strong aurora, you can sometimes see a layer of red light above the green glow, like in this amazing photo taken from the International Space Station. And here's what it looks like from Earth. This red color comes from another forbidden state of oxygen. Excited atoms in this state last an incredible 2 minutes before emitting a photon. This is possible only in the near vacuum of the upper atmosphere, where atoms are few and far between. Strong solar storms can produce other colors. The pinks and purples here are from nitrogen. Okay, Now we know the aurora's chemistry, which elements produce which colors. But how do these atoms get energized in the first place? There are no power plugs to produce electricity in the upper atmosphere. Well, the one thing more amazing than an aurora is a solar eclipse. The white area around the sun is the corona, a plasma composed of charged particles. In 1958, Eugene Parker realized that these particles could move really fast, fast enough to escape the sun's gravitational field. This means that the sun is radiating charged particles into space. Parker dubbed this the solar wind, and its discovery has reshaped our understanding of interplanetary space. The solar wind reacts with Earth's atmospheric gases and produces the aurora. Mystery solved. Well, not yet. We haven't explained why you only see it way up north in this ring formation. And it turns out that there's a southern lights as well. Here's a visualization of satellite measurements from an actual aurora. What gives it this characteristic ring-like appearance? In 1908, Christian Birkeland put a magnetized sphere into a vacuum chamber and fired a stream of electrons at it. The result looks very similar to a miniature version of the aurora. What's going on here? Well, Earth is basically a gigantic magnet. Its magnetic field is shaped like this, and it served an extremely useful function. It shields us from the solar wind, causing it to bend away from our planet. The solar wind also deforms the Earth's magnetic field, squishing the front, stretching the tail, and reshaping the field. Things get interesting when two of these magnetic field lines collide. This causes the magnetic field lines to break apart and reconnect. But they don't want to have sharp kinks like this, so they snap back really quickly, like a rubber band. Now, if there are free electrons in the vicinity, they get swept along and accelerated to the poles. Let's see that one more time. Each particle is accelerated along the magnetic field lines and hit Earth's atmosphere at insanely high speeds in a ring around the north and south poles, producing an aurora. This is one of a few ways particles can get accelerated to produce auroras. While the northern lights are usually visible only in places like Alaska or Iceland, solar flares like this can cause stronger auroras. This was the aurora forecast for May 10th, 2024, the strongest solar storm in decades. And I took the following photos in Seattle. These were taken with my mobile phone camera, quite spectacular. But to the naked eye, it looked more like this. There's just a faint hint of color, because in low light, humans see mostly shades of gray. I hope you've enjoyed this video on the science behind auroras.